Thanks, Harshi. This is the second of the innovation showcases we have planned for today. So this one is on quantum computing. I spoke in the beginning, we all must have heard about the immense potential quantum has, and a lot of people have doubts about are we ready for the next step in quantum computing, which is nothing but bringing quantum computing to life. And here in this session, what we will do is we'll talk about what we are seeing on the quantum side, how easy or difficult it is to leverage the power of quantum computing, because there are a number of cloud-based quantum services available where you can start using these machines immediately as of now, and not very expensive as well. And we will also show a couple of demos. We'll show one demo today. We have a few demos built. Today we'll show a demo of last mile route optimization in the case of logistics, and show and call an actual real quantum computer and show you some results from an interesting demo perspective. Now, quick discussion around introduction to quantum computing. We've seen the evolution of computing going from vacuum tubes to transistors to integrated circuits to microprocessors. And this is where a lot of the challenges related to Moore's law are coming up. This is where we believe quantum could be the next jump. Quantum computers are not meant to solve all problems, but there are certain problems which our quantum computing can solve better than any other computing systems available. These are problems typically in the area of optimization, machine learning, and simulation. And these are problems which are best suited from a quantum computing leverage perspective. And we'll speak about more in this session. Now, why are quantum computers more powerful? Why are they different? In a classical scheme of things, typically the compute systems are designed as bits, which are typically two states in a machine. In the case of quantum systems, they exist as qubits. They exist in multiple states. They exist in zeros and ones and multiple states at the same time. Some of these concepts of quantum computing are difficult to comprehend, so I would request to suspend your imagination, just go with the flow, and some of these things will become clearer as we speak more about specific examples. The Bloch sphere is an important constituent in terms of defining quantum systems, because the sphere gives you much more possibilities of combining multiple permutations and combinations for looking at a problem. So in the case of a classical computers, they process bits sequentially, whereas quantum systems are entangled, another concept which I'll speak about in a minute. So, in the case of quantum computers, there also answers are probabilistic in nature, depending upon the state of the qubits and when are you measuring some of those qubits. These all add to some bit of complexity, and this all adds to the fact that quantum computers traditionally have not been very, very reliable because they're extremely sensitive machines. And of course, technology has evolved a lot, matured a lot, and much more stable computers are available from a number of leading players out there in the market, and several of them have made those machines available from a commercial usage perspective. Three important properties of quantum computing. First one is superposition, which essentially means that the same particle can exist in two different states. This is the Schrodinger's experiment with cats. Interference means that two waves can go together. They can exist in phases, and one amplitude can exist at the same time as something else. And the last one is entanglement, and where the qubits entangle and influence each other. These three phenomena are leveraged extensively when we are actually programming around quantum computing. And typically, if you look at a quantum algorithm, this is how a quantum algorithm works. First one is you input the data as qubits. We are essentially looking at qubits, which gives you order of the power magnitude of ability to manipulate those qubits, not the traditional bits. Qubits gives you a lot more amplitude. I spoke about superposition, where you are essentially bringing the qubits to superposition, which essentially means that you're preparing the system to work across multiple states. That's the first step in a quantum algorithm. Then you get into entanglement, when you're applying the algorithm to all the states. So this is the entanglement phase. And then you amplify the probability of measuring, which is interference. And finally, you actually measure the results which the qubit provides you. Quantum applications, you find application of quantum in specific areas. Like I said, it's hardly unlikely you will find a mobile quantum computer 50 years down the line. You won't have that, but you will still have the classical and the quantum computers progressing in parallel, with quantum computers doing certain activities much more efficiently than traditional computers. So planning and optimization, logistics planning, manpower optimization, financial portfolio optimization. These are all prime areas for quantum computing. Recommendation systems, multimedia analytics, image, video, audio analytics, prediction engines, anomaly detection. We are doing some very interesting experiments. We are seeing much better results of anomaly detection and fraud analytics using quantum computers. With an emphasis, what you've done is it's not easy to build quantum algorithms because all the complexities I mentioned before. And there are various complexities additional to the fact that there are limited qubits available. It's not a very, very cheap technology. It's slightly expensive, and you pay by the number of qubits you use. You need to optimize the number of qubits and manipulate the various complexities. We have built a framework, a patent pending framework called EON, which essentially takes care of a lot of complexities pre-processing. So when you're bringing in your data to a quantum system to do the processing, the EON framework has already done its job to ensure that the data is ready and primed for a quantum system by leveraging all the powers of the quantum system. This is conceptually how EON works. In the interest of time, I'm not getting into detail. This is something we have filed the patent on. It essentially results in reduced training time for machine learning problems, need fewer qubits. It is also resulting in reduced information loss. So with the same amount of computing power and lesser cost, you're able to do a much more complex experiment using the emphasis EON framework. The demo I'll talk about is a capacitated vehicle routing problem. So this is a problem where you have certain depots from where you are going to distribute certain goods. Basically, consider the scenario of a logistics company where you have certain hubs from where you need to distribute the items to a last mile location. So you can see the screen I'm sharing now. This is the landing page for this quantum experiment where we are actually trying to do a last mile route optimization from a logistics perspective. Now, there are various modes to run it. I'm running a new experiment. I can choose between a truck of a fixed capacity or a varying capacity. For the sake of today's demo, I'm just putting it as a truck capacity as 100. I'm setting this as 100 and assuming that each truck which is going to distribute from a last mile delivery perspective has got a capacity of 100. And then I am going to upload a file which is nothing but the location where of the customer, the lat long information of the customers to whom the deliveries needs to be made. So basically, I'm uploading an Excel sheet where D0 is the depot from where the trucks has got to go and distribute these items. C1, C2, C3, these are all the customers to whom the boxes needs to be delivered. Let's assume that you are a logistics company who's going and delivering these goods and items to your end customers. There is a customer demand, which is the volume, and there are some constraints in terms of the way in which the customer is asked, I need to be delivered between 2 p.m. and 3 p.m. Those are all constraints. So basically, it becomes an optimization problem. The difference is you're trying to solve this complex optimization problem using quantum computing. I'm submitting this data to the quantum system. Here, the quantum system is not yet come into place. So this is how the entire image looks like. So the D0 is a depot of where the packages are going to be delivered from. Each dot here is a customer to whom you're going to deliver these packages. I'm doing assign vehicle. So this is where the quantum machine is being invoked. So we are actually calling through the cloud the quantum system of D-Wave, which is one of our partners, a close partner of ours who we are working with. Now, as we speak, it is going to the D-Wave quantum annealer and running our quantum optimization algorithm, given all the parameters, all the input parameters I just inputted. Give us a few seconds. It should be done anytime now. Now you can see that it's been pretty fast. It's already done its job. It's analyzed all this data which we inputted, and it is given you the order in which the various customers needs to be serviced and the number of vehicles you need to service it. And I'm now generating the routes. Now you can see that a complex problem like this, which would have taken typically a few minutes or a few hours, the actual quantum system has solved the entire problems in a few seconds. And you are right now gone from a bunch of packages you need to deliver to an optimized solution, and the engine is actually telling you in which order the vehicles needs to go and deliver. We have 5 vehicles the engine is allocated for you for delivery. Let's say I click on engine vehicle 1, it is telling you from D0 you go to customer 1, 2, 3, 4, 5 and 6. Similarly, you can look at every single vehicle. It also gives you cost breakup parameters, and it essentially walks you through all the ROI parameters it's already calculated so that you can take an informed decision about which vehicles should take which delivery. Thank you. Let me hand it over to my colleague Uday for the next demo and discussion around our cloud Krypton framework. Over to you, Uday.